Hello everyone. Guess who recorded this lesson once before and did not have their mic on? So I get to do it again, and there's no reason for any mistakes this time around, so should be all good. I'm well rehearsed. So today we're doing related rates problems. So in a related rates problem, we're given the rate of change with respect to time of one quantity, and we're asked to find the rate of change of a related quantity. To do this, we find an equation that relates the two quantities, and we use the chain rule, and implicit differentiation to differentiate both sides of the equation with respect to time. So general procedure for these types of questions, usually a good idea to identify what you know and what you don't, write an equation that relates all the variables, take the derivative of both sides of the equation with respect to time, and then substitute all known values and rates and solve for the unknown rate. So first example, you may recognize this as the area of a circle. Determine an expression for dA dt in terms of r and dr dt. So starting with this equation, we take the derivative of the whole thing with respect to time. So we would have dA dt equals pi times, so r squared would give you 2r, and then we got to do chain rule, dr dt, and that's it. Okay, no further simplification required. Question number 2, 4x squared minus 3x plus 5, determine an expression for dy dt in terms of x and dx dt. So again, we can take the derivative of the whole thing with respect to time. The derivative of this term would be 8x, and then you got to do chain rule, dx dt. Okay, and then that would be 8x dx dt. The derivative of this would just be -3, but you got to also do chain rule and do dx dt to that. Alright, we can further simplify this. Notice we have two factors, dx dt, on the right. So finally we would have dx dt times 8x minus 3. So that's final answer. Next question, number 3. V equals pi r squared h. Determine an expression for dv dt in terms of r, h, dr dt, and dh dt. So this is the volume of a cylinder. So what we need to do is take the derivative of the whole thing with respect to time. So the left side would be that. Pi, just the constant, and then we need to do product rule for r squared times h. So that would be 2r dr dt times h. So that's the derivative of the first times the second, and then you need to add the derivative of the second times the first, so dh dt times r squared. You could distribute the pi in there, so you would have then 2 pi r h dr dt plus pi r squared dh dt. And that's it. Next question. Pebble is dropped into a pond, causing ripples in the form of concentric circles growing in size. The radius of one circle is growing at a rate of 0.3 meter per second. Determine the rate of change of the area when the radius of the circle is 2 meters. So let's write what we know. So the radius of one circle is growing at a rate of 0.3 meters per second. That's the growth of the radius with respect to time. We need to determine the rate of change of the area. So we need to know dA dt when the radius of the circle is 2 meters. So when the radius is 2, we're dealing with a circle, so we know the area of a circle is given by this formula. All right, we've already done this before, so dA dt would be pi times 2r dr dt. And now we can sub in what we know. So we need dA dt when r is 2, so pi is fine. R is 2 meters, and dr dt is 0.3 meters per second. So basically just a plug and chug. So pi times 2 times 2 times 0.3. So when you multiply that all through, pi times 2 times 2 times 0.3, you get roughly 3.8 meters squared per second, right? And that makes sense because if you're multiplying meters by meters per second, meter times meter is a meter squared, and then you get seconds. So there you go. That's the rate of change of the area with respect to time. So if you're imagining this ring is growing, right, based on, so if you just were to measure the speed of this segment, right, it was at there, that means the entire area is changing by that much per second when you're at a radius of 2 meters. So next question, air is pumped into a spherical balloon. If the volume of the balloon is increasing at a rate of 20 centimeter cubed per second, how fast is the radius increasing when the radius is 30 centimeter? So let's pick out what we know. If the volume of the balloon is increasing at a rate of 20 centimeters cubed per second, so dV dt is that, 20 centimeter cubed per second. How fast is the radius increasing? So that would be dr dt when the radius is 30. So we have dV dt, we need dr dt when r is 30. What else do we know? So it's a spherical balloon. We know the volume of a sphere, that's on our formula sheet. It's 4/3 pi r cubed. We can get a dV dt out of this equation if we take the derivative with respect to time. And there will also be a dr dt in here somewhere as well. So let's do that. The derivative of r cubed, we would have a 3r squared, and then we got to do chain rule, dr dt. So dV dt is 20 centimeters cubed per second, so we can plug that in there, right? We know that. 4/3 pi times 3, and then the radius, we want to know what dr dt is when the radius is 30. So dr dt when radius is 30, so the radius is 30 squared times dr dt. So now we just need to isolate for dr dt. So we can multiply through all the numbers here on the right side. So 4/3 times 3 is just 4. And then 4 times 30 cubed, we can do that. So 4 times 30 cubed would be 3600 pi dr dt. And now the last thing that we need to do is isolate for dr dt. So we can divide both sides by 3600 pi. So 20 divided by 3600 pi gives us roughly this answer. So the radius is changing by that much per second when the balloon is at 30 centimeter radius. So that's actually quite a big balloon. It's maybe about shoulder width for most of you. So at when the radius is 30 and we're filling it with this much volume per second, if you were to track just a spot along the balloon, that's how quickly it's expanding, just along that line. So that's number 5 done. All right, number 6. The length of a rectangle is increasing at a rate of 3 centimeters per second. The width is increasing at a rate of 2 centimeters per second. How fast is the area growing when its length is 15 and its width is 8? So the length is increasing 3 centimeters per second. So dl dt is 3 centimeters per second. So we can maybe just imagine the outline of a rectangle, and then the width is increasing that fast. So dw dt is 2 centimeters per second. And what we need is how fast is the area of the rectangle growing when its length is that and its width is that. So we need this. So how fast is the area growing, changing with respect to time when its length is 15 and its width is 8? So that's helpful. We should probably come up with an equation that relates the width and the length and the area of a rectangle. And it's this, right? That's fairly familiar. And if we take the derivative of this whole thing with respect to time, then we can get what we need, right? So we need dA dt when the rectangle is like that. So dA dt when length is 15, width is 8. So nice thing about this equation is dA dt is already isolated for us. Okay, so we need to do product rule with this. So derivative of the first times the second times the plus the derivative of the second times the first. So dl dt times w plus l dw dt, and then sub in what we know, right? So dl dt we have up here is 3. W is 8, so that's the point that we're interested in. L is 15. That's the dimension of the rectangle at that point. And then dw dt is here, so that's 2. So just plug and chug. So we do 3 times 8 plus 15 by 2, 24 plus 30. Add them together, we get 54, and the units should be centimeters squared per second. And that works out here too, because this is centimeter per second, this is centimeter. So centimeter per second times centimeter is centimeters squared per second. So the units work out as well. Alright, on to the last question. Number 7. A water tank is in the shape of an inverted right circular cone, depth of 5, top diameter of 4. Water leaks out of the tank at a rate of that meter cubed per minute. How fast is the water level in the tank dropping when the water in the tank is 4 meters deep? So how fast is the water level dropping? So that's measured by height. So we need dH dt when the tank is 4 meters deep. So when h is 4, that's what we need to figure out. What else do we know? So it's an inverted cone, depth of 5, top diameter of 4. We know water's leaking out at this rate, so dV dt is 1/12. Okay, it's an inverted right circular cone. The depth Oh my. The depth is 5. The top diameter is 4, so that means we're dealing with a 2 here. It's a right cone. Volume is pi over 3 r squared times h. Okay, so we can find a dv dt in there. We can probably get a dh dt out of this term. So let's go ahead and take the derivative here. So dv dt is pi over 3. We need to do the product rule in here. So that would be 2r dr dt times h plus r squared dh dt. So at this point we have 1/12, and by the way, if it's leaking out, we could specify that it's leaving with a negative. Okay, so dv dt we have, great. Pi third, so we got constants. We don't know what the radius is when the height is 4, so that's something we need to figure out. We don't know what dr dt is at this point either. We know h, that's great. Again, we need r. And dh dt is what we're trying to find out. So we need a little more information. So let's at least start with what is the corresponding radius when the height of the water is there. We need to figure out what this radius is when the height is 4. So unfortunately I don't really have much more information other than I have this side. I need to figure out this side, and I don't have any more information to figure out. So what I can do first is maybe figure out what this angle is, and then once I know this angle, then I'm in a situation that I can figure out that opposite side. So in order for us to figure out this angle, we have the opposite, we have the adjacent. So tan theta is opposite over adjacent, 2/5. We can solve for theta here. We end up with 21.801 so on degrees. So that's great. That's a good initial step. And then the next thing we need is what's the radius when the depth is 4. So we can go now tan 21.801 so on, keeping that in my calculator, equals opposite, so that's the radius, divided by the height, which is the adjacent, so 4, so r is 4 times whatever this is. So tan of this thing works out to be 0.4 exactly, just because this, right? And then multiply both sides by 4, that's the radius. So it turns out that the radius is 1.6 meter when the height or the depth is 4 meters. So now we have that piece, which is great. So that's taken care of. The last piece that we need before we can continue to figure out what dh dt is figure out what dr dt is. We don't know what dr dt is. It should be related to the height though. So notice this equation here. This angle is going to be constant. This is the height. So it goes from 5 all the way down to 0. So the way that radius is related to height is this. So you can see it there. 0.4 times h. So we could figure out what dr dt is in terms of dh dt with this equation. So if we take the derivative with respect to time of both sides of this equation, we get dh dt in there. So everywhere I see a dr dt in this equation, which will eventually allow me to solve dh dt, I can just put a 0.4 dh dt in its place. Alright, so at this point we know all the elements that we need. We have that, these are constants, we have radius, we have dr dt, we know what h is, that's 4, and now we just need to figure out what dh dt is. So dv dt is negative 1/12. We do pi over 3 to 1.6 dr dt 0.4 dh dt times h, which is 4, plus 1.6 squared dh dt. So pi over 3 multiplies this whole thing and that. So next we can simplify a little bit. So just like if you multiply that by that by that by that and then divide by 3, you would get 128 over 75 pi dh dt. And then if you do that times that thing, 1.6 squared, you should get 64 over 75 pi dh dt. So next we have that dh dt, and then this inside the brackets turns out to be 64 pi over 25, and then it just remains to divide both sides by this, and we get dh dt finally. So that works out to be negative 25 over 768 pi meter per second, which is approximately equal to 0.0104 meters per second. So that question's done. Your assignment for today is in the textbook, and it's also here. So this is the one and only question I want you to do for today. You can submit it through Edsby. Just take a picture of your work. It's a melting snowball, so you can assume that it is spherical. And you know the surface area of a sphere. I believe it's on your formula sheet. So that one's yours. That's it for today. See you next time.